right?
Yes, sir.
Right. So we were discussing about the theoretical part of the microfluidic flows, right? And we briefly discussed about the different different definitions of mechanics, dynamics, kinematics, and kinetics. The four different aspects, four different terminologies that generally we come across, right? So what are those four terminologies that we come across? One is this mechanics. Okay, then we come across the word dynamics, right? In these two situations, we first worry about the natural laws. Okay, all the natural laws that we are first worry about, correct? And then from there, what we do, we come up with the governing equation, right? And these governing equations actually help us in solving, say, suppose, you may see a Wednesday, Friday class. As we finish, we will be able to really, derive an equation called the Navier-Stokes equations. Okay, so which generally governs most of the microfluidics flows. Okay, now if that is the case, now here it will see this is nothing but the Newton's second law. Correct? Now, when I develop the governing equation based on certain natural laws that are already existing, which is followed by, followed in certain certain, I can really identify a host of systems, okay, which generally follows these sort of laws. That is in the domain of mechanics and dynamics. They are used interchangeably, but mechanics is more of a kind of, it's more generic term, where dynamics has a little bit of, it's a subset of mechanics, right? Whereas you will see one term. I will show you actually as I go progress, how exactly you can do, we were doing some things, right? So suppose I take temperature, and then from there, I calculate temperature gradient, right? So this is more of a kind of like, interpretation. Say suppose I take a potential, right? I go for like, the velocity potential, which I define as the, say, minus of gradient of phi as the velocity vector, right? So these sort of operations, when we do, that type of situation is called the kinematics. Okay, in this situation, what happens? The geometrical arguments. We make use of the geometrical arguments, okay, in order to develop the governing equations. Right. So kinematics is a situation where I really don't go through this path. Okay, whereas I go through this particular part that is called the kinetics of the whole process. Right? Up to this point, it is clear to all of you. Now, say suppose I tell you that, say, I have a beaker. Okay, in that beaker, I have placed water. Right? In that water, I am putting one droplet of ethanol. What do you expect to happen here? I'm just dropping it in here. What do you expect to happen here? Anybody?
Sir, it will start forming bonds with water, sir.
it will start forming
bonds, sir, hydrogen bonds with water.
that is a little later. But what is the first phenomena that you expect? Say I give you another example. Say suppose I have another beaker where I have water. Okay, and say suppose I am dropping mustard oil here. So this droplet is mustard oil.
Then
Okay.
there will be two layers of liquid, sir, fluid.
So in mustard oil, you say that mustard oil will form a film on top of that, right?
Yes, yes, sir.
Okay. But for ethanol, what will happen? Will it form a film?
Mixing, I guess.
Also, it will mix.
Right. So ethanol, what will happen? Ethanol will mix with water, right? To mix with water, right? So here, I am behaving like a fortune teller here. Okay, I don't need to do any experiment, right? But then, if you tell me without doing the experiment, so suppose if you have oil, if you put in water, it is going to form a film, while it is going to mix with water, right? So how can I tell these two things? Any idea? How do I qualify this?
Yes,
Say,
sir, because
yeah. So how do I tell that? Say suppose I have two different systems.
yes,
One
sir.
system, yeah, follow. I have
Sir,
water.
because water and ethanol both are polar, sir, polar compounds.
Yes, this is water, and this is say C2H5OH, right? You have a drop, right? Yeah. How do I come to know that this is an immiscible system? Okay. And this is a miscible system. How scientifically I can really explain this thing?
So if delta G for mixing is negative, then it should be miscible, I guess.
Very nice. So I'm looking for a parameter called delta G, right? What is this parameter? Can anybody tell me what is G?
Gives free energy, sir.
Free energy. How is it defined?
Delta H plus T delta
H,
S.
H minus Ts, right?
Yes, sir. H minus Ts.
So why this is called free energy? Any idea? Free energy, but there is another additional thing is that free energy often, what type of system?
Isolated system.
Nah, open system.
Open.
Okay. U is the internal energy. U is equal to what? Internal energy, right? U is the energy of the closed system, right? H is what? H is equal to what? Enthalpy is U is the internal energy, right? Correct. H is what? What by definition? What is H? H is equal to U plus what?
U plus PV.
U plus PV.
PV. This is internal energy, right? And this is the pressure volume work, right? So now this internal energy is the energy of a closed system. So enthalpy is what? Enthalpy is what?
Enthalpy of
Energy of open system.
Is the energy of an open system. Very nice. Right? What is the difference between open system and closed system? Say suppose you have a pressure cooker, right? And you have put some curry dal and you are putting in flame, whatever. This is a type of typical closed system. Correct? Where energy is allowed, but no flow is allowed. I mean, of course, I'm assuming that the CT is not going up, right? At the top. That's a closed system. But moment this CT is up, moment the fluid comes out, that becomes an open system. Any type of engineering device, suppose there is a fluid flow through pipe, or suppose internal combustion engine, like in cars, okay, aircraft. These are all example of the open systems, right? So enthalpy is a measure of the energy that is available to you. That is for an open system. Internal energy is a measure of an energy of a closed system. Is it clear? Now you define two free energies. One is called A, which is a Helmholtz free energy. How is it defined?
The U minus Ts.
U minus Ts. So this is a free energy for what?
So closed system.
For a closed system. Correct? And delta G is what? G is a free energy for an open system, right? What do I mean by free energy? What is this Ts? Can anybody tell me what is S? What is ds?
S is the entropy.
S is the entropy. What is ds? How do you define ds? ds is equal to, by definition,
the amount of
reversible
energy due to randomness in the system.
dq reversible by t, right? ds reversible is equal to dq reversible by t, right? This is by definition. Correct? Am I correct or wrong? So what is Ts? Ts is what? It's a measure of what?
The amount of reversible heat.
Right? It's a measure of heat. Correct? Now, in a system, you have two types of thing. One is the total energy that is available to you. That is H. But Ts is the energy that is not available to you. So when you are, say, suppose you want to pay some money. Somebody needs a cash. Say now somebody comes and tells me that I need 100 rupees cash. But you have 10 rupees in your wallet and maybe you have 1,000 rupees in your bank. So that 1,000 rupees you are unable to pay. Why? Because you can't pay it cash because that is not available to you. Right now, all of you are sitting in a room, right? All of you are sitting in a room and there is this molecular motion is taking place, which is doing some work, right? But is it possible to extract energy from that? The answer is no. Say suppose the fan that is hanging on the top, is it rotating? Answer is no. The movement of molecule, the molecular say where am I sitting? The molecular movement around me, is it able to really displace me? No. Why? Because the amount of molecule hitting me from this side, the amount of molecule hitting me from that side, they're more or less similar, which actually stops my movement. Right? So there is no net movement from my side. So in atmosphere, there is some energy that is available to you that is not available to you to do some significant work. No engineering work is possible with this Ts energy. You cannot do much with this energy. This is a low quality energy. And H is the total energy of an open system. U is the total energy of a closed system. So essentially, if you really want to do engineering work, you have to look for what is the amount of free energy that is available to me. That is G and A. For an open system, this is an open system. This I'm looking for. What is the free energy available? Now, when delta G is negative means what? That means initially G and final G, which one is bigger? If I write Gi is initial G, Gf and final G, so which one is bigger? If delta G is less than Z, Gi is larger and Gf is lower. Correct? So initially you had a lot of potential to do work. Then what happened? Then you did the work and then all that available energy you converted into unavailable energy. From a very organized state, you went to a very disorganized state. Say initially this was pure ethanol. Initially this was pure water. But then moment to mix it, what happens? Water surrounded by ethanol, ethanol surrounded by water. They become, when there is no concentration gradient, there is no mixing. And that's the reason delta G becomes negative. The oil here spreads on top of that. So oil is phase separated from water. That's the reason, when the oil spreads on water, that's the situation where delta G is negative. In both the situations, essentially you are looking for the final configuration in order to really predict the final configuration. What you are looking for? You're looking for the thermodynamics. Okay, the thermodynamics of the system. That means whether you are looking for whether delta G is 0, delta G is less than 0 or not. Okay, so for a system like this, what am I looking for? I'm looking for, say, suppose if you have a beaker and say, suppose if you have water and if you have a droplet coming in, I'm looking at delta G less than 0 or not. That means I'm looking for the thermodynamics of the process. Okay. So you see the word dynamics is coming here. And thermo means, the energy. Basically, thermo means not only heat, all sorts of energy. So you are really looking at the contours of the energy contours here. Essentially, say, suppose, the free energy contour to see that whether this is a spontaneous process or not. Okay. So thermodynamics tells you what is the possibility here. But thermodynamics doesn't tell you what is the path, which way it is going to happen. So suppose I have taken a beaker, okay? I have taken 3 beakers, right? And I have water here. And I'm introducing alcohol from here, and alcohol from here. So whether the mixing process will remain same or different in all the 3 beakers?
Or maybe same.
Hello,
Yeah.
sir. I
Yeah.
have a doubt.
Hello?
Sir, G is equal to H minus T del S. Then here you said that T del S is insignificant form of
G equal
energy.
to
Then why we
H.
consider?
G equal to H minus Ts. Okay. Not T
Okay.
delta S. Delta G equal to
Okay.
delta H minus T delta S. Okay. So there is a difference between these two. So I'm writing the energy form. I'm not getting into this form. Right now, this is not under discussion. Okay. Yeah. G equal to H minus Ts. Yeah. Tell me.
Here Ts is insignificant form of energy.
No, I have
mean,
not said insignificant form of energy. I said that this is the non-available energy. This can be very, very significant. Say suppose
what is the significance of this?
Say suppose
If this is not available to us.
Say suppose you initially, so let us take 2 configurations. Okay. I'm drawing here 2 configurations. You have a beaker, right? You have 2 beakers. In this beaker, I have ethanol droplet here, and this is water. This is ethanol, this is water. Okay. And in this beaker, it is totally mixed. Ethanol is totally mixed with water. Totally mixed with water, right? So the question is that whatever is in the droplet, whatever is in the water, here in this system, and here in this system, if I look at the mass of ethanol, say suppose Me and Mw, and here also if I look at Me and Mw, right? They are same in both the situations. Am I correct?
Yes, sir.
Now, if they are both in both they are same in both the system. In this situation, moment this ethanol comes in water, what happens? You start a process called mixing. Correct? So this ethanol molecule will start getting accumulated around water molecules. Okay, while water molecules will start getting around the ethanol molecules. So it will keep dissolving each other, and there will be a walk done that will be going on for a while. Say suppose 5 hours, after 5 hours, you may reach to this situation where, every ethanol molecule is surrounded by many water molecules, and every water molecule is surrounded by many ethanol molecule, right? So it will be a uniform mixture. So in this uniform mixture, this is in a completely disordered state, right? Completely disordered state. Whereas this is in a completely, this is only ethanol, this is only water. Here, ethanol, water, they are completely mixed. So you are getting, see, this sort of situation where, this part, this entropy is very, very low. Why? Because I am taking pure ethanol, I am taking pure water. So this part is insignificant. I have the total enthalpy available for me to do the mixing. To this place, when it is totally mixed, since they have mixed with each other, now I don't have any energy left. This TS, this S has started going up, and this has become equal to this, and then this has become more than this to make that G2 less than 0. So then that becomes a spontaneous process. Am I clear?
Yes, sir.
So when you have, say, suppose when I have started pushing a car, I have full energy, I'm pushing. Correct? Now, as I keep pushing the car, what happens over a period of time, my energy goes down. And my energy, as my energy goes down, my capability to push the car goes down, right? So this is how you are going from available energy to the unavailable energy. When I take a matchstick and a matchbox, when the matchstick is separate, matchbox is separate. This is in a totally ordered state. You have your enthalpy is very high and entropy is 0. But moment I lit the matchstick, so now the matchstick is getting extinguished. It is generating fire, okay, and then slowly the entire matchstick is extinguished. In that situation, what happens? The total energy of the system remains constant. Total energy of the system and surrounding remains constant. But I convert a very ordered form of energy to a very unordered form of energy. Correct? So the balance from this to this only changes. So that's why it is said that, the entire universe is going towards a very huge potential at the start when initially the universe started, it's only the energy was there, right? But more we do work, we generate entropy. So whatever possible work is to be converted to entropy, moment you do something, it converts into entropy. So that's why, it's an irreversible process. Everything is very irreversible. Moment you generate some entropy, it becomes a irreversible process. So slowly you are going from a very ordered state to a chaotic state. Now, whatever is the chaotic state, that is the unavailable, that is the measure of unavailable energy. Whatever is the ordered state, that is the measure of the available energy. Is it clear?
Yes, sir.
You can ask the question. This is not very easy to conceive. You have any doubt here? Anybody has any doubt in whatever I have said? Please feel free. No? Should I proceed? Okay. Now, the problem that I introduced, say now I am doing the same experiment by mixing ethanol from one side, from the center, from the other side. Will the mixing pattern remain same for all the three? Yes, no.
Sir, I think yes.
Why?
Because the mixing doesn't depend, sir, on the side to which it is attached. The molecules are same throughout, sir.
Fine, but in this situation, the concentration gradient will be, this concentration of ethanol will be higher in this side. Here, the concentration of ethanol will be highest in this side. So this will go this way, and this will go this way, sorry, this way, and this will, in this one, this will go this way now. When the ethanol is dropped in the water, mixing will start from say, suppose right to left, right? Here, like, it will be both sides, towards right, towards left. But here it will be left to right. Am I correct? Am I correct? or wrong?
Yes, sir.
Now, if that is the case, then what am I dealing with? I'm dealing with the kinetics of the mixing. I know thermodynamically, I know they will mix. What Govindo is saying, that's that this will remain same. So that's the thermodynamic impression of, see, ultimately, if I wait for 5 hours, I may get fully mixed thing. Correct? But say suppose initially, if I look, say suppose I put a little bit of dye in the ethanol. Then I will see for this case, the dye will propagate from left to right. In this case, in both the directions. In this case, it will propagate from right to left. Now that is called the kinetics of mixing. So although thermodynamically something is a possibility, say suppose tomorrow morning, thermodynamically, the sun will ultimately come out, say 2-3 days later. But when there is a cloud, the sun may not come up. So that's a kinetics of the whole process. So thermodynamics talks about, say suppose if you are going on a train, say every station you will get a ticket counter, you get some food, okay, you get some passenger. So thermodynamics is about those stations. Say you start from Guwahati, you reach Delhi. It's a Rajdhani Express. Okay, 6 p.m., 6 a.m. In the morning, it will start from Guwahati. Next day at 10 a.m., it will be at Delhi. Thermodynamics will tell you this. But kinetics is every day the journey, what happens in the middle on the path, that is the kinetics of the whole process. Someday, it may get delayed. Someday there will be like, in the middle, the passengers are different. Passengers, the number of passengers who are traveling. So kinetic talks about the path with which, a process moves. Okay, it's basically the path of the whole process, whereas thermodynamics talks about what is going to happen, ultimately what is going to happen. Okay, if you are doing this course, ultimately what are you going to get? That talks about the thermodynamics. Yeah, Govinda.
Sir, then by this case, as you are saying, then we are not dealing with parts, sir. Initially, we will only have a look on this, sir.
You please repeat. We missed out the middle part.
Sir, actually, what I am trying to say that if I am not bothering about whether they will mix or not, we are bothering on the path only. Then we are looking only on the initial part of the time.
We are bothering on both. Okay, it's the kinetics plus thermodynamics makes the whole system. I mean, you will understand the whole thing. I'm bothering about both. I'm not leaving anything. What am I saying? That if you thermodynamically analyze the system, you are going to get only the end result. Okay. Now, if you analyze the kinetics of the system, you will know what will happen time to time, how things change. Say, suppose somebody has a matchstick and a matchbox, right? Now, this is supposed to lit the fire. Am I correct? But if you give a matchbox and matchstick to 5 different persons, you will see that 3 will be able to lit up, 2 will not. So thermodynamics tells that if I have a matchbox and matchstick, it is going to lit the fire. There is no doubt about that. There is adequate free energy available and it will lead to a negative free energy process. But kinetics tells me that, it depends on the person who is having the friction between the matchbox and the matchstick. If doesn't know the trick, they will not be able to really lit up the fire. And then, even if it is thermodynamically possible, sometimes it will not happen. Now you have to really worry about both. So you not only, if you just fuel the car, and then, if you purchase a best car in the world, it doesn't mean that, you are going to go to office in the right time. You have to make sure that there is a driver. You have to make sure that the car is started at the right time. It goes through all the signals and it reaches the office on time. So kinetics talks about those every nitty-gritty detail that you require in order to really make sure that the motion is leading to the destiny. Whereas thermodynamics talks about whether it's a possibility or it's a non-possibility. So suppose if I tell you, if I don't do any work, is it possible to put the water in top of the Himalaya? It is not possible. Thermodynamics will tell you not possible. If it is only possible if you put some work behind it. That means, say suppose you evaporate, that condenses as snow, and then it can really, cover the mountains. Is it clear?
Yes, sir.
Right. So 4 definitions: mechanics, response of physical bodies when subjected to forces and displacement. So, Hooke's law, Newton's law, quantum mechanics. So everything, is in this realm. Dynamics, the causes and changes in the motion, including the effects of the torques. Right. In that, kinematics is a part where we just don't worry about the causes. And kinetics is a relationship between the motion of the bodies and its causes, normally the forces and the torques. Dynamics has largely superseded the kinetics in science. Kinetics is still used in unsteady engineering processes. Unsteady, last line is very, very important. Like it talks about, like, what is going to say, suppose you say the mileage of the car is 25 kilometers, right? Per liter. But then when is that? It is in the 5th gear, it is on a smooth road. Okay, so then only 25 kilometers per hour. So that's a thermodynamic outcome. But say, suppose if you are running in a city, mostly in the 1st and 2nd gear, will it going to give you 25 kilometer per liter mileage? The answer is no. Who dictates the term? It is the kinetics, that is kinetics of the whole process that is dictating the term. Okay, is it clear? So you will find most of the, concept intensive, last 150 years, most of the concept intensive subjects are either classical mechanics or quantum mechanics or special relativity or quantum field theory. Okay, we are going to talk about classical mechanics and a very small part of quantum mechanics in this course. Rest of the things, you have to explore in some other course. Most of the things here will be Newtonian mechanics. At the end of the course, some of the phenomena will come, which is quantum mechanical in nature. Okay, relativistic we are not getting into right now because this requires a lot of control. You really need, Newtonian domain a lot of control before you really start dealing with the high-speed systems. Right. Now, if I really classify all the different types of flows, including macroscopic, microscopic, you can really talk about, I will give you examples, internal versus external, right? So suppose when the rocket moves, it's an external flow. Internal means, say, suppose the air conditioning in a car, that's an internal flow. Laminar versus turbulent. If there is a low speed flow, you will see it's an order. But if you go for a high speed flow, you will see that, there is a sort of chaos and disorder. So this is laminar versus turbulent. Compressible versus incompressible. When the density changes, it is compressible. When the density doesn't change, incompressible will come. Steady, unsteady. I just have discussed about the steady and unsteady. When, say, suppose when you are changing the gear from 1st gear to 2nd gear to 3rd gear to 4th gear, as slowly your speed is changing, that's an unsteady situation. Whereas steady means, say, suppose your accelerator is pressed in such a manner you are maintaining, say 50 kilometers per hour in your car. Supersonic, transonic, subsonic. Subsonic means less than sound. Transonic means up to 4 Mach number, and supersonic is more than 4. It is near sonic is transonic, subsonic is less than the sound, and supersonic. Why these 3 are important? Because, compressibility and incompressibility also has a connection with subsonic, transonic, and supersonic. Most of the supersonic flows, transonic and supersonic flows, are compressible flows. In that domain only, you will start seeing the change in the density. Whereas most of the subsonic flows are incompressible flows. Even air, flow at low speed, although air is an compressible fluid, but then it's very weakly compressible at low speed. Any example that air is incompressible? Can you give me any example where you can prove that air is incompressible? Air is compressible or incompressible, by the way? Hello, anybody?
Sir, it's incompressible, I guess, because there's no divergence in the flow of air, I guess.
Any example? How do you prove that air is incompressible? any sorry, any simple experiment you can do and tell me that air is incompressible. Say you take an empty bottle. Is visible? The bottle is visible to all of you?
Yes.
It's a blue colored bottle, right? You just, throw all the water out of it. And then, the top of this bottle, you cover it, you close it very tightly. If you press it, what will happen?
It will contract, I guess.
Will the volume change? What is your take?
Volume should stay constant, I guess.
Yes. So if the volume doesn't change, if you put a pressure, if the volume mass remains constant, right? The question is that say when I have bottled it very tightly, now and then close the top of the top cap very tightly, then the mass is not changing. It is constant. Mass is anyway not changing, right? Now, if the volume doesn't change, then what happened to the density?
Constant.
Density remains constant, correct? So that's the proof that moment you press it, m doesn't change, v doesn't change. That means it's a more of an incompressible material, right? It has a compressibility. Every material has even water has a compressibility, right? Nothing is incompressible. Incompressible is a very, very utopian idea. But then if you consider a fluid to be incompressible, the analysis, the equations, they become very, very easy as compared to when you consider a fluid to be compressible. So until or unless you are really compelled to deal with a compressible fluid, there is really compressible, properties are emerging, you should really not attempt in incompressible domain. So you should try and operate in the incompressible domain and then see if you are only compelled, then only you go to the domain of compressibility, right? So in subsonic situations, in laminar situation, in turbulent situation, in internal, external, most of the time we consider the fluid to be incompressible. We are going to learn how is it to be done. Only supersonic situations, we are going to see whether we use compressible or not. Even in that situation also, you can get away with most of the time with the incompressible treatment. Okay, until or unless you need very high precision movement, tracing and all these things. Single phase, multi-phase, just now we discussed mixing of ethanol is a single phase situation, whereas multi-phase is oil water type of systems are multi-phase. Elliptic, parabolic, hyperbolic, I'll come. This is based on the mathematical definition of the Navier-Stokes equation, and then Newtonian versus non-Newtonian. Most of the fluids like water, it's Newtonian, whereas there are modern science is all about the exploration of non-Newtonian fluids, like say suppose liquid crystals, like say suppose ionic liquids, like say suppose surfactants, like say suppose oils, waters, oils, different types of polymers, plastics, paints, these are all non-Newtonian fluids. So we'll explore, overall you will find like, these are the different types of flows and fluids that we are going to really consider in this particular course. So typical microfluidic system, how do they look like? So you may see that there will be a syringe, there will be a channel that will be drawn like this. Okay, so and then what you do, you inject with the help of a syringe, just like in our childhood, there will be a doctor who will be coming up with a syringe with some injection when we are ill, and they will put into our blood vessel or muscles, and then they will push. Essentially, that is what is microfluidic. Right, so typically I'm sorry, they look like this. It can be, say this is a bifurcated system. So you can have two bifurcation, each is getting bifurcated as it is going down. So these are the channel-based systems. So you can see that this is a red drop. It's flowing through with capillary action through this channel and going to this destination channel. So you can see three different types of fluids of three different diameters. It is moving. So this is more of a kind of channel-based microfluidics. And there is another part which is called the droplet microfluidics. So a micro droplet can also be a microfluidic system, right? So nowadays, there is a very beautiful concept that is coming up. It is called the digital microfluidics. So when there is a droplet, that is 1. When there is no droplet, then it is 0. And then you can really ordering these micro droplets, you can create the different types of binary languages, which is called the digital microfluidic platform. Okay. Micro channels are of different shapes. So this is a kind of straight channel. These are called also open channels. What is an open channel? If you have a microfluidic channel and if you don't have any top cover, it is open like this. So it can be straight, it can be like this, step function, it can be like triangular functions like this, repetitive. These are called the serpentine channels. Okay. So these are typical examples of different types of open microfluidic channels. Okay, so you can understand how exactly in a theoretical setup for an open channel we do. We consider a very generic. We are going to derive the equation for this, that there is an inclined channel. You do not know whether they are flat or whether they are inclined in terms of gravity. So that's why you have taken an inclined surface and the fluid is flowing on top of that. Say the thickness of the fluid is at h, and this is the surface, and the fluid is flowing at an angle of alpha. So this is the way you simplify the flow that is happening in an open microchannel. Whereas the closed microfluidic channel, they look like this. So essentially, you can expect in this type of situation, there is a top cover that is closing the top. So they look like this. There is a closed covered microfluidic channel. So and you are connecting this flow in a closed channel, right? And then they are flowing through the internal periphery. So you can, in case of a closed channel, what you expect? You expect there are confining walls to the fluid layer that is in the middle, and you have different types. So this sort of flow is called the Couette flow. This sort of flow is called the plain Poiseuille flow. Right. So slowly we will derive these equations for this sort of thing. So one of the major issues of fabric. So this is an example of a closed microfluidic channel with serpentine channels. You can see how many repetitions are there. This is a typical scale bar given. So you can see this is a matchstick, and the size of the entire microfluidic device is of the size of the matchstick. So many channels are that are embedded, right? So you use different types of lithography techniques. So how do you generally do? You take a surface and then through a laser beam. So this is called the micro machining through laser. You take a laser beam, and laser beam, what you do, you intensify on a surface. So a part of the surface, because of high intensity laser, that evaporates. Right now, once the high intensity, so locally, if you just focus there, what will happen? Because this light is exciting these atoms, so they will evaporate. So you just cut this surface through evaporation. But one of the major problems you may see that the cross section of the channel is not at all like either circular or a kind of rectangular, but they are away from that. Right. So when you are really using different types of channel fabrication processes, you encounter different types of these are some very idealization of the whole process, but ultimately they are not like this. Okay, or they are not like this. They are a little bit away from that because of the issues associated with the smallness of the smallness of the features, right? So now the dynamics, the interpretation, the concepts that need to be also changed with this sort of change in the morphologies, right? So instead of going for simpler things, typically in a microfluidic channel, you go for an arbitrary geometry, arbitrary cross section. And then, you develop your equations and boundary conditions so that, you are closer to the reality, right? These are some of the examples of the micro devices. Say, suppose, these are the points where you are dispensing. So suppose here you are reaging. Say I was talking about mixing, right? Say I put ethanol here, I put water here, I flow them together through the channel, right? I put some other reagent here, that comes, they mix. So this type of different types of microfluidics, these are called the lab on a chip platform. Like say, suppose in one place you put one marker, in the other place you put another marker, you mix them, you just develop the colorimetric signal, and from the colorimetric signal, you try and detect something, right? So this sort of things are called the micro devices, where fluid mechanic component, reaction engineering, okay, electronics, all these things, are integrated with each other to really give a device, small device, just like a glucometer, where, you put a micro droplet of blood, and that micro capillary drop, it gives you what? It gives you what is the glucose that is there in the blood, right? So this sort of devices are called the micro devices. Now the question is that if I really have to understand what is happening inside those capillaries, which are not maybe always a kind of like, rectangular or square or a circular cross section, then how do I go about it? Okay, so next 30-40 slides, what we are going to discuss, flat, a framework using which not only you can really see through all the fluid flows inside this sort of devices, but also you can really explore, you can really expand this knowledge base towards any type of compressible, high speed, and the quantum mechanical domain. Like, this will not be very different, the treatment. I mean, of course, the principles are very different, but the types of equation that you are going to handle, they will not be more complicated than that happens here, right? So essentially, if you really have to worry about the governing equations, the laws, you are operating in a domain where the Newton's laws are applicable, and you are going for mass, momentum, and energy conservation. Okay, you see that I have written very carefully here, mass, momentum, and energy conservation, whereas in case of entropy, I have written entropy balance. So there are two important aspects of this slide. Number one, can anybody tell me what is Newton's second law?
In order to create a change in the system, we need to apply an external force. So, and that external force is proportional to the acceleration of the system. So force equal to mass into acceleration.
No, that is not Newton's second law. What is Newton's first law?
Yeah. A system will continue in its state unless acted upon by an unbalanced external force.
Yes. Then what is second law?
Yeah. The rate of change of momentum of a system is proportional, is equal to force.
Yes, that is written on the slide. Now, question is that when you say the rate of change of momentum, whether it is linear momentum or angular momentum?
Linear, sir.
Anybody? When I say in Newton's second law, rate of change of momentum, right? What is that momentum? Is it linear momentum, angular momentum, or total momentum?
So for force, it is linear momentum, but for torque, it is angular momentum.
But how is it different? I mean, how do you bring in, say, suppose when you are analyzing something, how the aspect of angular and linear momentum both brought in when you do the dynamics? Any idea? First, is there a clarity that it is it rate of change of momentum when I say equals to the sum of the forces or torques on a fluid particle, right? So when I say momentum, whether it's a linear momentum or angular momentum, or it's a total momentum. Yeah, quickly, jaldi batao baba.
It should be total, I guess.
Yes, but where is this, angular momentum comes in when we really calculate them? Where is the angular momentum comes in?
If there is angular displacement like Rotation.
But when we are doing it, how do they come into our considerations? This is when we are doing it, when we are doing the formulation. So suppose I am using Hooke's law, right? Suppose I am using force balance. Correct. Where angular momentum comes in. So I raise this for first question that see the doubt between this momentum, total momentum, linear momentum, and angular momentum. So I keep this doubt alive for the time being. So there is a doubt, right? All of you have a doubt that, how these things are correlated in the first, how the second law is mapped to the Navier-Stokes equations. Okay, number one. And then where is this, doubt is creeping in, where this momentum, we will have full clarity of the entire momentum terms and all these things. This is number one point, very important in this slide. The number two is that when I'm considering mass, momentum, and energy, I call them conservation, right? Whereas when I'm going for entropy balance, I'm saying it's a balance. I'm not saying that entropy is conserved. Any idea why? Entropy cannot be conserved, right? Because entropy is a factor. That's why, generally entropy is correlated to the time. Time is one factor which is you cannot really conserve, right? So it always increases. It has a directionality associated with that. So entropy is such a parameter. Whenever you do something, whenever you do an engineering work, whenever you are doing an engineering work, what are you doing? You are generating some entropy. Okay. Minimum is the generation of the entropy. Maximum is the efficiency. Why? Then, you are going towards an reversible process. Right? But then if you don't generate entropy, the kinetics of the process is slow. Okay, kinetics will become very slow where, like, if your entropy generation is small. So suppose you want to make a car, it has to have a very high power in terms of movement in the beginning. Right? So those sort of things, entropy generation with small entropy generation, it is not possible. So in order to generate high entropy, you have to really compromise an efficiency parameter to make the process reversible. In order to really, you आपको सब चीज जल्दी चाहिए. WhatsApp पे message आप 10 दिन wait नहीं कर सकते. You need immediately. Moment you do that, you generate a lot of entropy, and that entropy generation leads to, that has a huge connection with the irreversibility of the whole process. More is the entropy generated. If the entropy generation is 0, then this process is reversible process. If the entropy generation is very high, then the process is irreversible. But irreversibility has an issue with immediate. Sir, मुझे अभी चाहिए. Sir, कब तक wait करवाओगे? So now these are, you are generating a lot of entropy. You are going for a less efficient process. Although, nowadays the interpretation is different. Fast means it is the most efficient. How quickly you can think, how quickly you can solve a problem. One moment you are doing, you are generating a lot of entropy. Now, old age school people will tell you to meditate, sit down and meditate. So there, what you are doing, you are basically trying to make the process very, very slow so that you generate less number of thoughts, right? So your potential increases, your available energy increases, your non-available energy reduces. So when you are generating more entropy, you are into more chaotic state. Whereas when you are generating less entropy, then you are into more ordered state. Entropy generation 0 means, I know, say sodium chloride molecule, face centered cubic, everywhere the molecules are placed. Now, moment you mix sodium chloride in water, sodium is surrounded by water, water is surrounded by chloride is surrounded by water. So this becomes a kind of a totally random, disordered structure, which has no potential. It's a salt water solution. where entropy generation is at the highest. So it's a very, very spontaneous process. But at the end, when you mix salt and water, it becomes a salt water solution, generating a very heavy entropy, going from a very ordered state of salt and water to a very disordered and randomly organized state of, say, mixture of salt water solution. Right? So that's the reason, entropy generation, entropy of the whole universe is already increasing. And you have to, why you are doing entropy balance? Because you need to know how much, you have lost efficiency in terms of the entropy generation. So this is the second factor. First factor is how do we convert Newton's second law, Newton's first law, Newton's third law, okay, towards the dynamics of the process. Second is, entropy. When I'm forcing, so suppose you say that when you apply force, something moves, right? Until or unless you apply force, the status quo will not change. If it is a stationary item, it will remain stationary item. If it is a moving object, it will remain moving without changing its velocity. Only when there is a change of velocity, then only, if you really want to change the velocity, you have to apply a force, then only the velocity will change. That is the interpretation of the second law. Right? And when you apply the force and the action and the reaction is always on two different bodies. That is the third law. Correct? So when we conserve energy, momentum, and mass, then we get into that domain. Whereas while we are doing that dynamical process, we generate entropy. More entropy we generate, we go towards the irreversibility and inefficiency. Okay, with the expense of fast and immediate. Right? The advantage that we have immediate. But now question is that if I am immediate, for the time being, it's a very short time advantage, but long term I have generated a lot of energy, a lot of entropy. Okay, so a lot of quality energy is being converted into lot of non-quality energy. Entropy generation means a lot of energy, which is, say, suppose you have a nuclear reactor, you have generated electricity out of it. So what you did, you converted into thermal power. That thermal power you have converted into what? You have converted into high pressure steam. That high pressure steam converted into, it started rotating the motors, and from there you have generated the electricity. The moment you perform all these processes, that uranium, thorium, whatever radioactive material, you have extinguished it. The moment you have extinguished it, you don't have any process to recover it back. So in that process, you have generated that, you have extracted electricity. Today, okay, you are able to really read books and all these things, but then overall entropy of the universe you have increased. So say suppose you have a bank balance of 1 lakh rupees, right? Now in that 1 lakh rupees, you have today extinguished 100 rupees. Question is how much you keep extinguishing so that it becomes 1 lakh, there will be no ordered energy available for the conversion to work. That's where this entropy balance is a factor. Clear? And the third important aspect of is that even at the level of 10 nanometer, which will be the lowest dimension we will arrive, you will find the fluid can be treated as a, in this particular course, whatever we are going to decide, the fluid can be treated as a continuum. Correct? So this is another factor, another confusion people sit with, that what is continuum? Continuum means, you can use average properties like density, viscosity, okay, thermal conductivity, all these average properties, electrical conductivity. So all these properties you can make use until 10 nanometer. Why? Because what is the typical atomic level? It is at the level of angstrom. When they form molecule, it is 5 angstrom, right? Now, 10 angstrom, which is 1 nanometer, in that level, molecular assembly start. So 10 nanometer to 100 nanometer is essentially the domain of the colloidal domain, where these are nothing but molecular assemblies, where the continuum model is still valid. Any questions in this slide? Any question? Should I proceed?
Sir?
Yeah.
Sir, is there any relation between entropy and time?
Yes. Yes, that is why you are yes, there is a entropy is a parameter which can quantify time.
Sir, how?
How that we have to derive. But then these are all, these are the two parameters, which is always what? Time is also increasing and entropy is also increasing. Total entropy of the universe is increasing always. Why? Because what is the entropy? Entropy is entropy initial. Okay, then entropy generation is equal to entropy final, right? So initially you are starting, say, suppose, okay, let me give you one example. How is it correlated to time? How can you correlate? There are algorithms actually you can find on the internet. So suppose you have a beaker, okay? And you have taken these glass balls. Initially, you have made them ordered like this. Okay, you have just placed them. Correct? This is time t equal to 0. I've just taken these glass balls and then I have arranged them like this, right? Then what I did, I have taken the glass, I have covered this with a at the top, I have just capped it like this. Sorry. I've just capped it on top of this like this. Okay? And then I just have shaken this. For say suppose t equal to say suppose 30 seconds. Right? So now when I have shaken this like this, so what is the probability that I get the same arrangement that I have started with? Is very high or very low?
Very low.
Very low, right? So I'll get a new configuration, right? Am I correct?
Yes, sir.
So now I again, I start with that 30-second configuration. Whatever change has taken place, I start with the 30-second configuration, and now I go for another 30-second to 60-second. I get another random structure if I keep shaking them.
Yes, sir.
Correct. So now what I am doing, I just plot whatever configuration entropy. I am able to calculate entropy, calculated based on what? The orientation. Initially, when I have arranged them, I can calculate the entropy initial just by looking at the positions of these glass balls, right? So this is the way generally entropy is calculated. If I know what is the position, say suppose I number them 1, 2, 3, 4, okay, 5, right? Similarly, I number all of them. Say 1, 2, 3, 4, 5, 6, right? So I number them. So this is 1, 1, 2, 1, 3, 1, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And this is say suppose 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, right? So based on the positions, I know what is SI. Then I know what is S30, right? Then I know what is S60, right? So in that process, if I can really say, suppose I create a continuous process, like I just keep shaking it and I have kept a camera. So from every second, I get the configuration and I calculate the entropy. Time is the y-axis because I want to determine time from entropy. This is the known parameter. This from the configuration, I am determining the entropy. Okay. And then from the configuration, I am determining the time, right? So you will get a correlation as I am doing the thing. Because as the configuration is changing, I will be able to really predict. So you can see that after doing some experiments, I will have a linear correlation and that will be able to give me what is the time that is associated with that. By the way, I just give you one very simple example. How do you measure time? How do you measure time?
So we can use a light pulse and see what and
this is an assignment. Okay. So next class you submit. How do you measure time? Like say suppose for length, you know that, right? So suppose there is a rod which is of the size of Bureau and Wetson measures, right? In France, right? So there is a kind of like, platinum iridium, right? This scale is there, which is like, kept at a particular temperature and pressure that defines meter, like kg, meter, mks, whatever we see, right? So there are some of the standard materials that are available, which we consider as meter, this, that. How do you measure time? What is the modern way of measuring time? Okay. Submit this as an assignment and then try and correlate that with entropy. Okay, this will be an assignment. So essentially you will see, I think this is the cesium, right? This rotation is called the cesium battery, right? The calculation of time, right? So you will get it, that this is called the Cesium Standard, okay? So this is the way generally people like, this is the, my A is visible, right? It's in National Physical Laboratory, UK. Okay, Cesium Standard is a primary frequency standard where photon absorption by the transition between two a hyperfine ground states of cesium-133 atom is used to control the output frequency. Okay, so you will be able to really see how these electronic transitions are used for this particular time measurements, and then try and have a feel of the entropy associated with that. Okay. Is it fine with all of you? Yes, somebody say yes, no? All are silent.
yes,
All are there or not? Yeah, my things are not responding. I'm moving, right? In your
yeah,
Yes,
but
sir.
right now it's showing. Yeah, we can see the slide right now.
see the slide, but you can't see me. Am I correct?
No, sir, we can see you too.
But then I am not moving, or am I moving?
Right now it's working fine.
Great. So now let us go to the domain of, see this we did a part of it, right? So I don't want to redo it. So C is a function of X, Y, Z, and T, correct? All of you are comfortable with this, right? What is a partial derivative? If I make the other variables constant, right? If I make all the other variables constant, so suppose when I'm differentiating with T, if I make X, Y, Z constant, then that is a partial derivative, right? What is a total time derivative? The typical derivative that we take, that is the total time derivative. But there is a thing called the substantial derivative. What we did this, that say suppose you have a variable, say suppose phi, which is a function of X, Y, Z, and T. So if I really want to know what is d phi, what should I do? Del phi by del T, X, Y, Z, dt, then
Del phi by del x yz t dx
bolte raho.
plus del phi by del y xyt. No, xzt. Sorry, xzt. Del phi by del z xyt dz.
Right? Now, in this, what I do, I divide everything by T. What will happen? Into what? Am I correct? Am I correct? Dx by dt. So I say this is u velocity. I'm going fundamentally. See, this is called the kinematic argument. I'm using kinematics here. I have defined a function. I have put forward a mathematical rule. Okay, how to go about that? And then what am I doing? Dx dt, x directional change with respect to time I call as u. It's a scalar. Dy dt is v, and dz by dt it is w. Right? And then what I do, I write del phi by del t plus ui vj wk into what? Dot product of del phi by del xi
plus del phi by del yj
j plus del phi by del z
k cap.
k. So what should I write? I can write del phi by del t plus u
v dot del
gradient of
phi.
Clear? So let me see. So this derivation is clear to everybody, right? So I can write this as the substantial derivative or the total derivative d phi by dt as what? Del phi by del t plus v dot gradient of phi. This gradient is a vector operator, right? Now in this situation, if you have v, which is, say, suppose u vw is a vector, is the velocity vector. Okay, and this is to be 0. What will happen to this?
Second term will be 0.
So this will become 0. So this will become del phi by del t. Right? So any variable phi, this can be temperature, this can be pressure, this can be x directional velocity, this can be z directional velocity, this can be y directional velocity, any scalar phi. The variation of that particular scalar phi is dependent on two things. One is the variation at a particular point, x, y, z.
With respect to time.
When I fix that particular point, how that parameter is changing around that. That is the del phi by del t. This particular term is called the local variation. Okay. Local variation means I have already fixed x, y, z, and I want to know with time in this particular point how things are. Say time t equal to 0. What is the situation? Time t equal to 30 seconds, 60 seconds, how things are changing. So that variation is called the local variation. Okay. Whereas v dot del phi needs a movement. If there is no velocity, if there is a static fluid, this is 0. If the car is not moving, this v is 0. If the aircraft is not moving, this v is 0. But if it is moving, then this term comes, this variation comes. This variation is called the convective variation. So convection associated with that. Say suppose you have the Brahmaputra river, right? The Brahmaputra river is there, right? So suppose the Brahmaputra river is stagnant and I have put a football on the Brahmaputra river. What will happen to the ball?
It will flow with the river.
No, if there is no flow, it's a stagnant water. The Brahmaputra river in winter dries, no? There are small ponds, there is no flow, water is stagnant and I have a ball there. What will happen to the ball?
It should stay in place, I guess.
It will stay in the same place. Newton's first law. If you don't apply any force, it is going to stay in the same place. If the river flows, then what will happen?
It will flow with the river.
It will flow with the river, right? Now, when something moves with the velocity of the medium, right? That is called the convective motion or advected motion. Say suppose this particular water here, stationary, there is no motion, right? So there is v equal to 0. So if at all there can be an acceleration, then it can be only local acceleration, nothing else. Whereas if there is a fluid motion, right? Now, if there is a flow, then if there is a variation of any property like temperature, pressure, velocity, that is called the convective variation. And these two aspects, they come from where they can really be modeled very easily using what? So C is, if C is the concentration, you can see that this part is the local part. This part is the convective part. So this part is associated with the convection and this part is associated with the local. The total, these two combined together, this partial and this combined together is called the substantial time derivative. Substantial time derivative, okay, which takes into account this capital dC by dt, takes into account the entire amount. If something is moving, right? So the entire amount of movement. The example here is given. Say suppose partial time derivative, right? Suppose we stand on a bridge. That means XYZ is fixed. And I'm looking at the concentration of fish just below the bridge. So some fish has come. They are fighting for this, food that I have given. Now, if I stand at a particular place, and if I look at the variation of the fish movement, so that is called the partial derivative. What is total derivative? Now, suppose we jump into the river with a motorboat. I am also moving with a motorboat. Fishes are also moving. So that is called the total derivative. Correct? Now, substantial derivative is that my boat is stopped. My boat is moving just with the river motion. And then I am observing the fish concentration. So that is called the substantial derivative. So there are three ways of looking at the whole thing. One, I am stationary. So when I am looking at it, I am stationary. That is a partial derivative. When I am moving at my own speed and the dynamics is happening at its own speed, that is the total time derivative. Whereas if I am moving with the motion and trying to see what is the change in the dynamics, that is called the substantial time derivative. This is also called the Eulerian way of interpretation of the variables. So typically you will find we will follow this Eulerian dynamics in terms of the interpretation of different types of fluid motions, microfluidic motions. Any question? Any question? No. Okay, great. So that brings me to the statement of Reynold transport theorem. So first thing what we define is a control volume. Okay, I'll come back to this slide. What is a control volume? So say suppose I want to really know what is happening in a river or an aircraft, okay, or in a car or in a micro channel, okay, or in any type of situation where there is a flow. So what I do, I really look at different types of systems, and from there what I say that I'm not going to really worry about different types of systems. I first worry about a part of this system. I first worry about, say, a part of this system which I call as a kind of a control volume, a differential volume element. I just show you. Sorry, that picture. Say suppose this is a control volume. Okay. Suppose this is the volume, total volume. Now here I choose a control volume dV. Okay. Now I do everything around this dV, this control volume. And then what I do, I integrate over the entire volume. Now, if I integrate, if my physics is correct in this control volume, and if I integrate over different geometries, so this particular, if my physics is correct, then what will happen? This particular control volume can be extended for pipe flow, microfluidic channels, blood vessels, okay, to aircrafts, to Brahmaputra river, to any river, to any type of fluid dynamical system. So essentially, Reynold transport theorem talks about the domain of Newton's second law, all the Newton's law that is applicable to this control volume in a manner like this. What is that? So Reynold transport say that in a particular volume, any change of property is associated with three different components. One is change of that property. So here N is extensive property. That means is the total property. And rho eta is, when you have this property, the same property per unit mass is eta. When you divide N by mass, you get eta here. Okay, so you are looking at an extensive property N. Say suppose if N is mass, so what are the properties that we will be attempting? We will be attempting mass, momentum, energy, and entropy. Okay, entropy we just leave it. Mass, momentum, and energy. And in all these three, you may see when mass by mass is 1, momentum by mass is velocity, energy by mass is specific energy. Right? So eta is essentially the specific property, which is by mass, and N is the total extensive property. Say suppose this is mass, suppose this is momentum, suppose this is energy. So first is in the total control volume, whatever is the change. And second is if I just add all the fluxes through the faces of the control volume. So you saw that cubical box. So from the faces, whatever fluxes are going out, all the fluxes if I add over the controlled surface, right? And third is if there is a movement of the boundary, the fluxes associated with the movement of the boundary. So there are three different components associated with this. Number one is the change in the control volume. Number two, the fluxes that are coming out of the surfaces. Number three, if there is a moving boundary, which is a more complicated. Generally, here we will not consider, most of the problems will consider to be fixed boundary problems, right? So what are the different types of fluxes that are going out of the surfaces? Altogether, we can consider that should be the change of the system. Change, I mean, the substantial derivative is nothing but the addition of these three components. This is what is the statement of the Reynold transport theorem. Now, how do I prove it? So first what I do, I define a system, like say suppose a car or a kind of aircraft or a microchannel. I define a control volume. Okay, these are the examples of the control volume. And then what I do, I enforce the laws of mechanics. Conservation of mass, conservation of linear momentum, conservation of angular momentum, and conservation of energy in that control volume. Okay. How do I do that? Very simple. First I identify the extensive property, that is mass, momentum, and energy. This is my extensive property. And then what will be my intensive property? For mass, it is 1. For momentum, it is velocity. For energy, it is specific energy. And then what I do, I take this into the Reynold transport theorem. But before that, we have to prove this Reynold transport theorem, right? So this is the proof that you will see that, this one is the initial configuration. Okay, this has been taken as a moving boundary only, just to make sure that you have the full proof. So this is the boundary 1. This is initially control volume 1, and then after some point of time it has gone to 2. So initially system is the control volume, and after that is T equal to T, and T plus delta T you have CV minus 1. This it has left and this it has procured. So CV minus 1 plus 2 is your T plus delta T system. So any property B system is what? BCV minus B1 plus B2. Now what you do? You look for the change with time. So T plus delta T minus T by T. Okay. So I just request all of you to submit this entire thing as an assignment next day, because there are certain tricks that you will miss out if I just read out like this. If you do it, then it will be very, very handy, right? So what is the change of B? Change of B is T plus delta T minus this. Now T plus delta T I have already written. T also have written. So I put those things here. Correct. So from this page, this is T plus delta T. This is T plus delta T. This is T. I just replace it here. Now, if I replace back on top of this, what happens? I get dV by dt as this is the change in the control volume. This is the change because of what? the amount of B flowing out through the control surfaces. And this is because of amount of B flowing through the control surface in delta T, right? So you can see that there is a component that is coming out to be 1, and there is a component that is coming out to be 2. So this one part left out, and these two part that has come in, so that has been reflected in these two. Okay. Now, if I put delta T tends to 0, this becomes dB by dt, which is my substantial or material derivative. Right. Now you see how do I calculate the volume part. So BCV minus at T plus delta T minus BCV at T by delta T, which is dBCV by dt. This can also be written as ddt of control volume beta rho dV. Rho is what? Mass per unit volume. dV is what? Differential volume of the control volume. So beta is what? Property per unit volume. If you do a volume integral of that, so what happens? This volume goes off. See, this mass per unit volume into volume. So mass into this, what is the total change of this across this volume, right? So this can be interpreted like this. Now, if I take the fluxes, how do I go by the fluxes? You see that the mass out is rho into the control volume. So what is this control volume? You can think about an area delta A dot delta ln. Ln is the normal, right? Ln is the normal. Normal can be in any arbitrary direction, whereas velocity can also be any arbitrary direction. And then if you define an arbitrary angle theta between them, so you may write delta ln as delta L cos theta, where delta L is V into delta T. Delta T is the time. So now if you multiply and take a dot product with that, so what happens, dB delta V, that you get delta A dot V into delta T cos theta. Okay. Now, what is delta B out is beta into delta M out, and that delta M out you place here from here, right? So once you do that, so what happens? B2 comes out to be this, right? And then, if you just, integrate over towards all the control surfaces. So, if you simplify this, that comes out to be B dot out comes out to be beta rho V dot N dA. How does that happen? Let us go step by step. So B2 T plus delta T is dB out. dB out, from the previous expression, we keep beta rho V cos theta delta T dA. Then we put B delta T tends to 0 to see, divided by delta T, how much is the total change. So, we get B rho V cos theta dA. Now V cos theta is nothing but Vn, from where only the V dot N originates. So essentially B out becomes B rho into V dot N dA. So the third term also comes out to be in a very similar manner. So delta M in is rho dV. Delta V, again, I put the same set of arguments and I get the same set of expression from there. Okay. And then, BI is BI, if you just, put in here, you get the same set of equations like the previous one, only with a minus sign. Now, if you assemble them together, the change is what? The total change in the control volume. This is the one surface which is going out, and this is associated with the surface in. So this is the total Reynold transport theorem that is coming out to be for a fixed volume. Correct? So I just request you to to do these entire steps. All the steps are given. You do in a piece of paper and submit. So next day's discussion will start from this one and we'll go for mass balance, momentum balance. And I think we will solve Newton's law and then we will solve so Friday we will solve the equations for the flow. For Couette flow and for this sort of flows, right? Yeah. Any questions you have? Hopefully by Friday, I think we will be able to really go through. Apart from the viscoelastic part, we will be able to really finish up to. By Friday, we will be able to finish up to this slide 77, right? So your assignment remains to be, to finish the whole thing up to the slide 29. So it will help me in browsing through very fast up to 77. Yeah, any question you have? Hello, any question? Any question? Have you understood things? Is it clear? No.
Yes, sir, it's okay for the moment.
Go through this. I will revisit once again. Once you do once, I'll go through once again. Okay. So thank you for today. So let us meet on Friday again from 6 to 7:30. And then next Wednesday, we have these presentations. Okay. Yeah. Thank you so much. Bye for today. Happy Republic Day to all of you. Now, hopefully you